Hi, everybody. Welcome to Lecture 2. And before we dive into our Orgoland material today, I just want to remind you that if you haven't posted your life story yet, really go to our Sakai site and let all of your tour group members, including myself, know a little bit more about you, since this is going to be quite a journey in Orgoland. And the more we get to know each other, the easier this trip will be. So here's pictures of my family and my two daughters, which are our dogs, and the rest of my family. So go read about my life story and please post yours if you haven't done so already. The other thing I'd like to let you know is today is kind of one of our wrap-up days for intro chem material, but that doesn't mean that you in 2 lectures are going to become an expert in everything that you need to know from the intro chem section that's related to Orgoland. So what I've posted on our Sakai site is a beautiful folder. Oh, maybe, there we go. A beautiful folder full of websites that can address each specific topic we've been talking about. For example, today we're going to talk about hybridization, a little bit on MO theory, and definitely a huge chunk of resonance, which is something I don't want you to avoid. Even if it was painful in intro chem, it is vital in Orgoland. So we will learn to conquer our fear of resonance and learn how to play with it in a better way. Okay, so let's get busy. And I just can't stand starting with nothing but intro chem land. So as you can see from our goals today, we're going to dabble in a little bit of Orgoland first, because I just love Orgoland. So we were looking at things like formulas that you're going to see in Orgoland and for structures. And part of Orgoland is going to be trying to get you to determine the structure when given a formula. So what I want to be really clear about is one formula does not always mean one structure is possible. So this formula C2H6O could actually generate these 2 legitimate octet rule Lewis dot structures. And I think that you should know the functional groups that are in these 2, right? Have you got your Post-it notes yet? Really? Did you put them all up? Are you starting to learn them? Because there they are in my dungeon of a new office in my basement of my house. I put my functional groups up there. See, they're all up there. So please feel free to start getting these functional groups in your head, because then you'd be able to look at these 2 and know right away that you have an alcohol and an ether. So that would be one way of making sure that you have different compounds from one another, is they have different functional groups, different connectivity. Okay, so what's so different about these? Well, they're built differently. They have different connectivity, and therefore we are going to call them structural isomers of each other. So isomers is the name for compounds that are built differently and have different connectivity. Okay. The reason we want to be aware of these is because of the different connectivity, one being an alcohol, one being an ether, they will behave differently chemically in our Orgoland environment. For example, this is ethanol. Start practicing our nomenclature, 2-carbon chain ethanol. It's a liquid and antiseptic. The antiseptic part comes in all sorts of different forms, including beer and wine. But if you were to start digesting this ether, ooh, bad news for you. First of all, it's gaseous, where ethanol is not, and it is highly poisonous. Do not try to consume dimethyl ether. Okay, so structural isomers are going to be really key to our kind of looking at formulas in Orgoland and being able to determine their chemical properties. And just to beat this one to death, structural isomers, as you can see, are not the same compound. So we'd have to write them both for this molecular formula. And they have different properties, as you can see, and they will react differently, as you can see. So let's be on the lookout for structural isomers. For example, can you spy whether these 2 molecules are constitutional, otherwise known as structural isomers? All right, I'll pause and you give it a shot. Okay, so now you unpause. So let's see if you came up with the same answer I did. Now, the danger in looking at these is they look different, but when I'm trying to figure out if they're structurally different, then I need to start looking for, say, the backbone of the molecule, and I actually start numbering it. So I number this one carbon 1, 2, 3, 4, 5, 6. 6 carbons in a row, and coming off carbon 3 is the 7th carbon. So trying to number them and their connectivity means that carbon 3 has to have carbon 7. So I'll try it. I can do left to right, right to left, but I'll start left to right. 1, 2, 3, 4, 5. Wait, but connectivity, I'm just going to continue my backbone, and it's just like it raised its hand. Instead of going out on the left, this molecule raised its hand and put carbon 6 above it. And then coming off carbon 3 is carbon 7. So these two molecules are equivalent, and the danger is now that you can see I can raise my hand, or as molecules do when they raise their hand, they go from, say, this conformation where the CH3 is on the bottom, and due to the single bond here, they can rotate without breaking any single bond and just rotate this molecule around and redraw it in a slightly different way. So you can see all these single bonds will rotate, and we could get all different kinds of drawings of this carbon chain, but I haven't broken any of the bonds. So no matter how I redraw this, it would be the exact same molecule and not a structural isomer. Now, granted, if I pulled and break the bond off and then attached it somewhere else, now we're talking structural isomers. Okay? How's that feel? Cool, I like that. There's a little taste of Orgo land, and we're actually going to learn an instrument that you're going to be able to play with in lab, quote unquote lab. We'll show you an instrument that actually could tell you if you have a structural isomer or not, and tell you which structural isomer you have. It's very, very cool. I'm very, very excited about that instrument. Another thing that will help us understand how to build our structures from a formula to make sure that we have a possible structure that fits the Lewis dot structure rules, an octet, is something called degrees of unsaturation, which we'll abbreviate DU. So sometimes I'll get formulas that are a little more complicated, like this one, C2H2NOCl. So how do I know how to build this one? Is there a structural isomer for it? Well, DU can come to your rescue a little bit. So DU is a way of calculating whether your molecule has double bonds, triple bonds, a ring. All of these represent some form of unsaturation, where you've had to remove hydrogens off of the structure from the maximum amount that you could put on it to make these double, triple, and rings. Okay, so an example of that is my chain that I just showed you was all over the place, but if I want to turn it into a ring, then I have to literally take this hydrogen off and say the hydrogen on the other end off, and then once I take 2 hydrogens off, then this molecule can close into a ring, and I have a degree of unsaturation. Okay, removing 2 hydrogens to make a ring, removing 2 hydrogens to make a pi bond, a double bond, same thing. So that's what we can help us in terms of drawing the formula. Now, granted, for any formula that's just carbons and hydrogens, there is a equation we can use. Oh, a little math. Woo! Okay, so a little math that'll help us figure out the amount of degrees of unsaturation in our molecule, where N represents the number of carbons and X is your hydrogens. So let's play. Let's try it or something a little simpler than our C2H2NOCl. Let's try it with C6H6. So take a second, see if you can use the formula and come up with the same DU I do. Stop. Go. Okay, so when I plug the number of carbons and hydrogens into the formula, I get a DU that is equal to 4. Hopefully you got the same thing. What does a DU of 4 mean? Oh my God, it means you have lots of unsaturation in your molecule. Boom, and you could have like 4 double bonds in C6H6. Such a small little molecule with so much unsaturation. It's impressive. So what I want to get across to you now is a DU of 4 is also a big signal. Alarm should go off. Ding, 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 ding. DU of 4. Oh my God, Nick said DU of 4 is most often going to look like this molecule. Ooh, sorry for the squiggly bonds. But it is a 6-membered ring, which is 1 DU. And then 3 double bonds, which makes up the other 3 DUs. Benzene is a very common structure that we're going to see in Orgoland, and it has an extremely high amount of DUs. So if you ever see a DU of 4 or more, then start thinking benzene, okay? The other thing I like about DU is if this formula was wrong, let's say I'm trying to develop a formula for a compound, I'm not quite sure. If I have a DU that is not a whole number, like 0, 1, 2. If I get a DU that's 1/2, that's negative 1/2, negative 1, these are all signs that my formula is wrong. There's no way you can build a structure if your DU is not 0, saturated, 1, 2, 3, or 4 with some degree of unsaturation. So be on the lookout for this. This will save the day on lots of situations that you need your DU to be a whole number. Oops, sorry. This should be this. I want it to be a whole number. DU equals whole number. That's good news. If it's not, that's bad news. Okay? Cool. So what happens if my formula is not as pretty as just CnHX, like the one I'm asking you to draw a structure for? So here's some tricks on how to convert C2H2NOCl into a formula that is just CnH, so that you can actually not have to remember every single formula that is in the textbook, but just this one. So if I have a DU, if I have a formula that contains a halogen, a Br, for example, then when I look at halogens, Br, the Lewis dot is 7, according to your periodic table. Notice it's going to bond at only one spot, which is exactly what a hydrogen wants to do. So these two are equivalent. So just change your formula temporarily for the DU calculation and add a hydrogen in place of the halogen. Okay? Very nice. That seems nice and straightforward. What about if I had an oxygen? Well, we just saw dimethyl ether as our structural isomer. And notice that this has no unsaturation. And notice that if I were just to remove the oxygen and bond the 2 methyls, it's as if that oxygen didn't exist at all. So really, you can ignore oxygen in your formula and not worry about it for your DU calculation, because it's just sticking in the middle between 2 atoms and never causing a degree of unsaturation or not. Never taking the place of a hydrogen or not. Just being stuck in the middle between 2 bonds. Okay? Now, nitrogen's a little trickier. So I'm going to let you know right now, this is not in the textbook, as you can see, but this is something that I can show you in class. Right now, I'd like you to trust me that if you see a nitrogen, you want to substitute this nitrogen for a CH. That a CH is equivalent to a nitrogen in any molecule. And I can show you why in class. So for C5H5N, I would convert it to C6H6, which we just proved should have a DU of 4. So C5H5N has a DU of 4. All right. So what's the DU for C2H2NOCl? Pause. Take a second, see if you can figure this one out, and see if you get the answer I do. Okay, welcome back. And the answer is this DU is 2. If you didn't get a DU of 2, please make sure to ask in our class and our study groups how we calculated the DU to be equal 2 and how to convert C2H2NOCl into an actual C2 or a CH formula that you can use to plug into just this one. Just that one formula is all you need to know. So that's the key to this process. Okay? Cool. All right. Now that you know this molecule has a DU of 2, see if you can come to class with an actual possible structure. And we'll see how many structural isomers your study groups come up with in different ways to put C2H2NOCl together using octet rule, Lewis dot structures, and every single one of the structures you draw needs to have a DU of 2. Okay? A little review, step back. Remember that isomer problems? Okay, let's see if you got these. Take a second to try this problem and see if you can spy whether which pair are structural isomers here. Okay, now we're back and the answer is D. Ooh. If you didn't get D, come to class and ask us why. Let's prove it in class. Okay, cool. Feel free to also take a look at these and confirm for me in class what the DU is for each of these molecules so that we're straight about degrees of unsaturation. All right, we're jumping into the deep end. Welcome back to Intro Chem land. Now, I understand everybody has different levels of comfort, understanding, knowledge in all of these areas from hybridization to molecular orbital theory and resonance. So this is in no way do I expect this brief little lecture to teach you everything you need to know from Intro Chem land, but I hope, my hope, is that it just pokes some memory cells in here and stimulates a little neurons flying off that go, oh yeah, I sort of remember that. And if you don't, then please take a look at those websites that I've posted in our Sakai site under the resource section for review. And please ask questions in study group this week for what is going on with these hybridizations and things like sigma and pi. These are really important concepts that we need to know. So I'll pause, take a second, and see if you can answer the questions written on this slide. Okay, we're back. Woo! Just like that. Okay, so these are the answers I got, and let's see if you came up with the same ones. The hybridization of the oxygen. This oxygen is sp2. The hybridization of this carbon, even though it is written so ugly with just 90-degree bond angles, it is sp3. The hybridization of this green carbon is sp2. And the Lulu of them all, the hybridization of this nitrogen, drum roll please, I could put in music, but I won't. Drum roll please, is sp2. Oh, this one, the nitrogen is a little odd. We're going to take a serious look at this nitrogen in a few slides. The sigma and pi bonds is molecular orbital theory when we no longer can use atomic orbitals or hybridization like S and P. So really a pi bond is this little double bond up here has one pi bond and one sigma bond. So this molecule has one pi bond and 1, 2, 3, 4, 5, 6, 7 sigma bonds. Okay, let's go play with these ideas a little more and see what's going on. So hybridization is a model of the molecule that helps us understand the fact that I can't use these atomic orbitals to explain the bonding that's taking place in this molecule. Because if I were to look at the experimental data, what bond angles do we usually see for, say, this tetrahedral carbon here? As I mentioned on the last slide, are they really 90 degrees? No. But if I use the atomic orbitals, notice these are all 90 degrees to one another, and therefore there's got to be something happening between the atomic orbitals of carbon, and then when it starts bonding, they must switch, hybridize, move, change. Some new model of the orbitals must take place. Otherwise, all my bond angles would stay at 90 degrees to one another, especially when I use my carbon that has 4 valence electrons, 1 electron in each of these atomic orbitals. So this is going to help us explain why it went to 109 degrees, is that it really must be some hybridization of all of these s and p orbitals and no longer becomes atomic orbitals once I move to the molecule. The easiest way for me to show you how this is actually taking place is for you to understand and ask yourself, can you tell me, was that bond right there, which electron dot in the carbon was it using? And which electron dot is in which of those atomic orbitals up there? Was that electron in the S, or the P, or the PY, or the PZ? Can you specify which p orbital and which orbital, atomic orbital, that bond was using? No. Look at all 4 electron dots look exactly alike. So really, this dot at the top could be an S. Oops, excuse me. Could be an S. This could be P. This could be P. And this could be P. So I could be using those and assigning them there. But do they have to be? No, right? This could be the S, and this could be the P, and this could be the P, and this could be using a P. So I'm not quite sure. Wait, maybe it's the other dot that's in the S. Oh, wait, as you can see, maybe this is the S, and this is the P, P, P. I'm not quite sure. Wait, oh my God, chaos, that's the S, and that's using the P, and the P, and the P. And so really the odds are that each electron could be coming from any 4 of these orbitals. And so since we don't know which one, then we hybridize them and say, oh, it's really an average of all those possibilities, and therefore is sp3, a hybridized average of the possibilities of where the electron could be coming from. That's the easiest way for me to spy why this carbon is sp3. Now, you guys might have learned that shape, knowing that it's tetrahedral, gives you the hybridization sp3. Totally fine. I love using shape to help me figure out hybridization. But I also like using this idea, which will come to bear really soon when I have to unhybridize one of these hybridized orbitals, and it will not be the S. So it'll help us understand how, say, this pi bond is formed and which orbitals are being used to create that. Okay, but at this point now I have a new bond, a new idea. It's called hybridized orbitals, and the electrons live in these and can space themselves out, since they're no longer in atomic orbitals, as far apart from one another as possible. And that makes our nice, beautiful tetrahedral. And so we love hybridization. Ooh, okay, sorry, bad joke. I don't even know what that animal is. Zebra horse? How would you call? I don't know. That's it. Very interesting. All right. So how do molecular orbital theory fits in? What are those pi and sigma bonds all about? They help us understand the pi bond especially, okay? So let's take a real close look at this pi bond, because that terminology, even pi, is a new terminology that hybridization can't actually express. And so this new molecular orbital theory is to help us understand double and triple bonds a little better. So I'm going to take the same molecule and try to show you what has to happen, if you don't remember, for pi bonds. I can make this original bond between the carbon and the oxygen, directly between the two nuclei. So I can stick two electron dots directly between each other and form a bond in between each other. This would be known as the sigma bond. A sigma bond is any time the electron bonding pair is between the two nuclei. But you can see, to establish my octet and form the next bond, I have to use these two. And there's no way that they can sit in between the two nuclei. So I have to then unhybridize one of my p orbitals. And I'm just going to play with the pz because it kind of matches the direction here. It doesn't have to be the pz. But I unhybridize one because to form that pi bond, I can only do it with p orbitals. P orbitals only. And what's often forgotten about this is the two p orbitals that form this bond have to be parallel to one another. They're both pz. So pz, pz. So that they are on the same plane so that they can overlap with one another. Very, very important. We often forget that when we make these pi bonds. We just think any two p orbitals are going to overlap. But in our chemistry world, for spatial orientation, it is incredibly important that we realize that the pi bond is going to have to overlap and get them on the same plane so that we can create this beautiful delocalized set of electrons that are no longer bound to any one atom, but are now one new pi bond that actually exists above. That pair exists above and below. They're flying back and forth all around that sigma bond in the middle. And so this is going to be our, pi bond. Oh, sorry. Okay, so I just want to emphasize this pi bond here is going to have to be parallel. Did I say that enough? Parallel p orbitals. And in doing so, then I have now unhybridized it. And that's why this oxygen had a hybridization of sp2. Okay. But we'll take a look at why the nitrogen is sp2 as well. But first, let's have a commercial break about carbon double bonds. Commercial break, little twist and shout, yes. See, so sometimes these lectures need a little pick-me-up right in the middle. Why not? Commercial break. Okay, let's talk about these double bonds and their rotation. Because when we were playing around earlier with our structures, we talked about how single bonds love to just be rotated everywhere. Can double bonds do that too? Well, let's take a look. So, the strength to break both the sigma and pi bond, boom, it's been measured. Experimentally, it takes 145 kilocalories per mole to break both the double bond and the sigma bond. If we just tried to break just the double bond, okay, to rotate it, that would take 81 kilocalories. I mean, excuse me, just the single bond, not double bond, just the sigma bond. So we look at another molecule, and if we just broke the single bond, and so by difference, we can calculate how much energy it takes to break the double bond. The double bond takes, therefore, 64 kilocalories per mole to break that double bond. And the reason I want to look at that is because that's what's got to happen if I'm going to rotate my molecule. Let me show you. I have it in my background. Did anybody notice my pirate ship? Pirate ship. Pirate ship. If you look close, there's Captain Mole, who's actually running the pirate ship. And therefore, there is a pi bond that lives on my pirate ship. This is a pi bond between two p orbitals that are parallel, and they're overlapping here and here. And therefore, I cannot twist around these two here because they are tied together, and they require 64 kilocalories of mole per mole to break them apart, which maybe I have in this world. Except, as you remember, sitting right here at room temperature with me, there is only basically enough energy to generate 20 kilocalories per mole of energy. So really, not enough at room temperature to break this bond. And so it's very, very important that you recognize that pi bonds cannot rotate as easily as single bonds. They are stuck here. And that will bring us a big new area of structural isomers, because if they're stuck, notice how this CH3 and this CH3 are on opposite sides of that double bond. And I can't just willy-nilly rotate that bond methyl up to the top without breaking the double bond. So it won't. It will stay there. And therefore, I have a structural isomer that could have the same connectivity, but putting the methyl on top from one double bond and on the bottom in another. Whoa. You're going to get to that kind of structural isomer a little later in the course, but I'm just warning you now that this might be a cool little commercial with some cool groovy music. But in the end, it's going to have a huge consequence to us, and I just want you to remember it now that we're talking about pi bonds. They do not rotate. All right. Let's get back to the business at hand and that tricky little nitrogen and why it was sp2. Because I bet a lot of you wouldn't have imagined it to be sp2. So here is why this bond is sp2. Resonance. That negatively charged nitrogen is very uncomfortable being totally negatively charged, having a full charge on it. And if it can spread that negative charge to any other atom in the molecule, it will do anything in its power to do so. And I mean anything like unhybridizing a p orbital and putting the pair of electrons in a specific p orbital like the 2pz, so that it can actually align itself with the pz orbitals that are forming that pi bond. And then it can do resonance. It can move this pair of electrons and start overlapping between this middle p orbital, but that middle p orbital is already bonded with the one. So it has to take its electron and give it out here to the other p orbital, as you can see. So now the oxygen can become negatively charged. Whoa. Resonance. So let's take a look at those resonance structures from these parallel p orbitals of 3 atoms in a row. And I really want to emphasize that resonance for you in the past might have been very confusing, but if you just look at resonance as something that has to take place between 3 atoms in a row, no matter how big and complicated the molecule gets, focus on the charge and see if you can move it to an atom 2 atoms away, 3 atoms in a row, okay? It's nice that it doesn't actually do anything different. Once it does this resonance and moves this pair, either pair of electrons, one can form here, kicking the other one out there. Then what you've really formed is a new molecule. I wonder if I drew it. Nope. Okay. A new molecule that puts the negative charge out on that oxygen, a double bond to this nitrogen, and now it only has 1 lone pair and 3 bonds. It is neutral, 0 formal charge, and now the negative charge is on the oxygen. So these two are in resonance with one another. They are resonance structures of one another, and therefore the charge is being spread out, as you can see by this green drawing over here, up there, that all 3 p orbitals overlap and spread out all 4 electrons in those pairs between 3 atoms. And in spreading out that charge and spreading out those electrons, we've delocalized those electrons. They're not locally attached to any atom. And in doing so, you have created an incredibly stable resonance structure. And resonance will stabilize that negative charge, and we give it a special name called conjugation. This is a conjugated system. And anytime you can take a charge and spread it through resonance, You have stabilized that molecule and it'll do so. Now, when we did that, notice what happens to the hybridization if I were to ask you in this new resonance structure what the hybridization was of this nitrogen. And you saw that it had a double bond, single bond to the hydrogen and a lone pair. I think you would have a much easier time telling me that that's sp2. The danger is you might look back over at this oxygen and think it's sp3 all of a sudden, but no, it has to remain sp2. Both of these atoms have to keep a p orbital available to do this resonance. So both of these atoms, the nitrogen and the oxygen, will be sp2 hybridized so that they can have a p orbital to make their pi bonds in the resonance structures. What's the takeaway here? The takeaway is do not just look at an atom and do your Vesper pairs and determine hybridization without checking for resonance. If the molecule atom, has resonance, its hybridization will change. And that is something that I think is a little new to a lot of introchem hybridization that you've learned, but something that's very important in Orgoland. We will need to keep this in mind. And therefore, if resonance plays such a huge role, let's talk about some of the rules for resonance for the remainder of this class. And some of these will look familiar, but I just want to make sure we're all clear about them. And some will be like, what are you talking about? Of course I wouldn't do that. Well, for example, of course, rule number one is that resonance does not involve the moving of atoms. As you saw on the last slide, I'm moving electrons only, and only pi bonds and lone pairs. I will never move a sigma bond. So this is totally wrong. There's no way I can just pop that hydrogen off and resonate it all the way up. There's what? Oh, that makes me feel bad. But I could do a little resonance with that lone pair on the nitrogen, fold it in to a p orbital that's involved in the pi bond between the C double bond O, and push out the pi bond onto the oxygen. This creates charge. We'll talk about which one of these two resonance structures would be favored in the world, but they both happen. So keep in mind, they both happen. And since they both happen, what does that mean the hybridization is of that nitrogen? Yep, sp2. Okay, so keep that in mind. Rule 2, each resonance structure must have the same number of electrons in total charge. Please do not play superhero and create charge out of nowhere. Charge cannot be created or destroyed. So if this is a neutral molecule to begin with, notice the plus and minus cancel each other out. The whole thing has to be neutral at the end. Please make sure you label and put charges on your resonance structures to make sure rule number 2 is abided. How about rule 3? Stability of these resonance structures is judged by the same thing in Lewis dot. So basically, if you have an octet for every atom in your resonance structure, it's going to be very happy. And you can see the fine print here is if you start out with a molecule that does not have an octet, and you're wondering like, how the heck can that happen? Well, we will see carbons, for example, with only 3 bonds attached to them and a positive charge. But this carbon will try to do resonance as much as possible to move the charge off that carbon and gain a 4th bond. So it might start with less than an octet, and therefore one of your every resonance structure you create could have less than an octet. Keep an eye on the number and location of formal charges. These have to all balance out. So let's take a look at this molecule. This is an azo compound. This nitrogen-nitrogen bond, this is not a functional group that I'm going to have you put a post-it note about, but it is called azo. And they're really popular in synthetic dyes. So all those beautiful colored powders are all azo compounds that are slightly different, that produce slightly different dyes that make up all the bright colors in our clothes. They're really kind of cool. Tidbit. So this has charge on this molecule though. Can you do resonance? And I think you can, because we have 3 atoms in a row. We have lots of pi bonds and lone pairs. And so I could take the electron pair on the far right, nitrogen, move it in with that arrow, as you can see, and move another pi bond out onto the carbon. Now, out of these two resonance structures, which one is the most stable? You should look at electronegativities. Who wants to be negatively charged? In these two examples, this one is very stable. It has the charge on the negative charge on the nitrogen, where if you look at the one on the right here, it has the negative charge on the carbon. Periodic table should be handy. If you don't have a poster of one on your wall, just have a periodic table somewhere, because these electronegativities are going to become very, very important. And so knowing who is the most electronegative atom way up by fluoride, and anybody close to fluoride is more electronegative than anybody further away. Okay? So these two are definitely possible resonance structures, but one is still favored over the other. A resonance structure I would want you to stay away from, and this is the problem with resonance for some of you, is you're like, I have no idea when to move a pi bond, when not to. Here is when not to move a pi bond. Notice this is just the red arrow moving this pi bond out, and all it did was make more formal charge. Just increase the charge all over the place. There's no reward for the molecule to do this. Why would it do this? It's not moving the same charge around the molecule, it's making more. So do not do this. This is awful. Okay, I won't emphasize that now. The actual structure of the molecule resembles that most stable resonance structure. So that middle one in the last slide is 90% of the time going to exist like that. 10% maybe puts the charge on the carbon. And I'm totally making up those numbers, but you get the idea. Okay? The resonance stabilization energy increases as the number of important resonance structures increases. Important meaning real, logistically possible and moving charge around. So let's take a view of this. This molecule is again starting with a carbon with only 3 bonds to it. So it has a positive formal charge. It has an empty p orbital is what it is. But I see a pi bond right next to that empty p orbital. 3 atoms in a row, pi bond. So let's do a little resonance. Oh, and so I can move this pi bond and move the positive charge to here. But notice it's next to another pi bond, so I move it again. Try to show each resonance structure as you go. Some of you will love to want to do this to here, but what you've done is you've missed the one in the middle that shows that the positive charge could exist on this middle carbon as well. So as you're doing resonance, treat it 3 atoms at a time and show the actual outcome of that 3-atom rearrangement of the electrons. Okay? A little tip that you already might have picked up on is we've been showing these little arrows to show the movement of electrons. This is going to be huge, huge in Orgoland, that we're going to show the movement of electrons because, as I mentioned in the very first lecture, there's only one thing that will get you through this course, and that's to remember plus loves minus and minus loves plus. The one thing is a positive charge can't jump. What a positive charge is something that's missing electrons. And so what we're going to do is move electrons in this course. Push electrons everywhere. So we will push electrons towards a positive charge to make it less positive. So to do that, we will use these arrows, and they will always start, as you can see, at the source of electrons and go towards the lack of electrons. That's the direction every arrow will take. And this is what all of our organic chemistry is about. So this molecule is very stable because that one carbon on the end doesn't have to hold that positive charge all the time. It can spread it out throughout this molecule. And therefore, this is called resonance stabilization of the molecule. Take a look at this. See if you can tell me which pairs here are resonance structures of one another. I'll pause. Okay. And the answer is, drum roll please, there is only one. Come to class if you want to see why. We'll answer it in study groups. Here's another one. And instead of giving the answer to this one, I'd like you to bring the answers to this to our study groups and bounce them off everybody in your study group before I show up to your study group. A little word of warning. For some molecules, like the one on the bottom over here, the very bottom one, there is a possibility of doing resonance in two directions on this molecule. I see a negatively charged atom in the middle of the molecule, and it might want to push the charge to the right, and it might want to move it to the left. So feel free to draw resonance structures for one side of the molecule, and then start with the original structure and draw resonance structures going to the other side of the molecule. You can have resonance structures going off in two directions. If that makes it easier for you to show me all the ways you can spread this negative charge. Notice 2 out of 3 of these have charge. Please try to only show resonance structures that move this charge to different atoms on the molecule. That's the main purpose of resonance. That's the main goal of it in our course. It will have purpose now, meaning in your life, glory. Can you move charge? And only that one in the upper left actually has no charge, but you've been very familiarized with this. And if you can name this functional group by now, you have already got it up on your post-it notes. You're doing awesome. So I'll see you in class. Lots of questions. Bring them all. Let's get intro chem clear in our head, as clear as it can be for what we need for orgo. Okay? All right. See you soon. Bye.